So the idea that we did with combinations without replacement doesn't work because the actual combination we select is going to affect the number of ways in which that we can permute them. So let's see what we can do. We're going to view this problem slightly differently. What we're going to do is we're going to use the same idea that we had before, which is we're going to write the combination in a way that is sorted. So instead of writing the set as 1, 2, 1, I'm going to always write it as 1, 1, 2. That will just give me a systematic way of writing what I want to do. So let's imagine that I have elements 1, 2, 3, 4, 5, 6, and 7. And from here, I'm going to get a selection which is 1, 1, 2, 5, 5, and 7. So I'm going to think of this as 1 is selected 2 times, 2 is selected 1 time, 3 is selected 0 times, 4 is selected 0 times, 5 is selected twice, 6 is selected 0 times, 7 is selected once. And that's how we are going to do the computation that we are going to do for combination with replacement. So as I said, we are going to imagine the problem slightly differently. What we're going to do is we're going to think of n buckets and we're going to throw r identical balls in it. So you can see that I have these buckets and I'm throwing r identical objects in it. So when I throw these balls, what I will have is some balls will fall in the first bucket, some will fall in the second bucket, some will fall in third bucket, some will fall in fourth, some will fall in fifth, and so on. Some buckets might be empty. So we are going to say if the xth object has m balls, then we are going to choose x m times in our collection. So if I look at this, the first object I'm going to select 1 time, the second object I'm going to select 3 times, and so on and so forth. So how does this happen? Now we are going to view this problem a little different again. We are going to look at this as a number that has n plus 1 minus r bit number. The balls are going to represent 0 and the divider is going to represent 1. So how many dividers I have? The number of dividers I have, I know. That is basically the number of buckets that I have. So in this case I have n buckets, so I have n minus 1 dividers that I need, and I have r balls, so those r needs to be put somewhere, and that's going to give me a number that has n plus r minus 1 bits. In those I want r zeros and I want n minus 1 ones. So essentially I have this one large number that has n plus r minus 1 bits, and I need to figure out which r of those are going to be zeros. So that's going to be given by this combination in this corner. I have n plus r minus 1 possible bits, of which I need to select r of them, and I want to assign them to be zeros. The rest will be ones, and that will give us the answer that we are looking for. Note that once I have this number that is n plus r minus 1 bits long, I have figured out which objects I have in my combination. Namely, figure out how many zeros I have over here. That's going to decide how many times I'm going to select the first object. How many zeros I have here, that's going to decide how many objects I'm going to have of the second type, and so on and so forth. Note that we have some situation like here where there are no zeros in the middle, and that means those objects are not going to be selected at all. This slide is quite dense, so what I would suggest is maybe you want to review this slide one more time, and if there are questions, please ask them in class as well as on PSI, etc. Let's review a couple things from the previous slide. One thing I want to mention is we created a number that was n plus r minus 1 digit long, and we decided where to put zeros, and that's why we got the expression as c of n plus r minus 1 comma r. This is going to be same as c of n plus r comma n plus r minus 1 comma n minus 1, and this would be equivalent to choosing the dividers that we are going to put in the middle, to choosing the ones that we are going to have. Let's look at an example from before. So before we had 4 objects, we are going to select 3 with replacement allowed. So we had n is equal to 4, r is equal to 3, and so if we put this formula, we would have gotten c of 6 comma 3, and that would have given us that there are 20 combinations, and it's exactly what we had on the slide earlier. This is a table that will describe the formulas for different ways of doing permutations or combinations. So if replacement is not allowed, this is something we saw in an earlier module. The number of ways that we can do this is NPR or NCR, and we had these formulae for that from previous module. This is what we just saw. Namely, if I wanted to do R combinations, but replacement is allowed, then we thought of this problem in a different way by thinking of this throwing balls in a bucket and then constructing an R combination out of it, and we got the number of ways that we can do this is c of n plus r minus 1 comma r. R permutations is actually much simpler, because if I'm allowed to choose the same object more than once, then I can essentially choose the first object in n ways, second in n ways, third in n ways, and so the total number of choices we are going to have is n to the power of. Here are some other variations of the same problem. I'm not going to go through the details of each one of these. This is something that I would ask you to keep with you as a reference, because it tells you about a lot of different variations of this problem, and we will look at how these variations show up in different problems. So all of these refer to throwing a bunch of balls in a bunch of cells or buckets, and this varies in terms of whether the balls are distinguished. The way to think about what distinguished means is that they have numbers, say for example, or they have different colors, etc. Whether the cells are distinguished, in other words, are the cells put in a way that this is cell number 1, this is cell number 2, this is cell number 3, or are these just some boxes that if we move around the boxes it's still the same set of combination? The third one is, can the cell be empty? And that will give you some variations. And the last column gives you how many ways are there to place R balls in N cells. So the simplest case is the first one, in which case each cell can be empty, the balls are distinguished, the cells are distinguished, and that means that for every ball you have n different choices. Taken together we have n to the power r. This is the second instance where you are required to put at least one ball in every cell, so no cell can be empty, in which case the answer is this n factorial times s of Rn, where s of Rn is this formula down here. Now this formula, if you think carefully, you would see that it is basically an instance of the inclusion exclusion principle that we saw earlier. All that it is doing is it is generalizing it for any large number. Then we have these four other cases that talk about whether the balls are distinguished, cells can be empty, etc. Some of these, so for example, these two refer to the S formula, which is the formula that is given below here. These two refer to the combination formula that we looked at for permutation combination without replacement. So in this, this is something that we saw earlier, that here the balls were not distinguished, the cells were, and the cell could be empty, and that gave us C of n plus r minus 1 comma r. This is something that you should be able to derive on your own if you think about it a little bit. And the way to think about this is, if the cell cannot be empty, then you put one ball in each cell. The balls are not distinguished, so it doesn't matter which one you put where. And now you are left with fewer balls, and you can now put them any way you like, and you don't have to put any extra balls in any of the buckets because each one already has one ball. So essentially that allows you to change the values of n and r, and to be able to solve this problem. I want you to do this problem to see why this actually works. Once again, we have reached the check before you go ahead slide. I want to tell you that because of lack of time, we are unable to prove the claims in the last two slides, but please keep a copy of this during the exams, because what would be important is you identify what type of problem it is, and then you can look up the table to figure out which formula to use.